Not a metaphor, not sci-fi. A hole in space, connecting two points in the universe that have absolutely no business being connected. And here's the thing nobody actually tells you. If you fell into one, if you really fell into one, what happened next would depend entirely on something Einstein figured out a century ago that physicists still argue about in hushed, nervous tones to this day. The question isn't whether you'd survive. The question is which version of you comes out the other side. Here's the thing about wormholes. They've got a technical name, Einstein-Rosen bridges, named after Albert Einstein and his colleague Nathan Rosen, who pulled them straight out of general relativity's field equations back in 1935. They looked at the math and found something deeply unsettling. The equations didn't just allow for black holes. They allowed for tunnels, connections between two completely separate points in space-time. The math worked. The physics? That's where it got ugly. Here's how to picture it. Take space-time, the four-dimensional fabric that everything is made of, and fold it. You're holding a piece of paper, and you bend it until two points that were far apart are now millimeters from each other. Now punch a hole through both layers at once. That's a wormhole, not a curve, not a slope, a hole. And here's where it gets terrifying. The version Einstein and Rosen originally described, it wouldn't stay open. It'd collapse faster than light could travel through it. You couldn't use it. You'd fall in and the tunnel would close around you like a fist. So the real question, the one that's kept theoretical physicists awake since 1988, is this. What would it take to hold one open? And what happens to the human body that tries to find out? From a distance, a traversable wormhole wouldn't look anything like you expect. No fire, no crackling electricity, no dramatic sound. There's no sound in space. What you'd actually see is gravitational lensing taken to its absolute extreme. The stars behind the wormhole's mouth would ring it, their light bent into a perfect halo, and the interior wouldn't look black. It would look like a window, a circular opening onto a completely different piece of the universe. Astronomers call this a photon sphere. Light literally orbits the structure, looping around its throat before escaping. It's honestly one of the most beautiful things physics predicts, and that beauty should make you nervous. You'd be staring at two locations in the universe at the same time. Just sit with that for a second. Two places, one view. The human brain was not built to process this without short-circuiting a little. But here's what nobody tells you. The closer you get, the more the geometry around you starts to misbehave. Space near a wormhole mouth isn't flat, it curves. And depending on what kind of wormhole you're dealing with, Schwarzschild, traversable, rotating, that curvature does very different things to the matter traveling through it, including you. Here's where your body becomes the experiment. The critical measurement isn't the wormhole's mouth, it's its throat. The narrowest point, the bottleneck. And for a wormhole to be traversable, that throat has to stay open, held against the ferocious desire of space-time to collapse and seal itself shut. The only thing that can do that, according to the equations, is something called exotic matter. Not dark matter, not antimatter. Exotic matter, a theoretical substance with negative energy density, meaning it pushes space-time apart instead of pulling it together. Gravitationally repulsive at a fundamental level. Now we have observed something called the Casimir effect, a tiny measurable demonstration of negative energy between two metal plates in a vacuum. It's real, verified, peer-reviewed. But the amount of exotic matter you'd need to hold a wormhole open wide enough for a human body? Physicists estimate it'd have to be comparable in magnitude to the mass energy of an entire star, held precisely, indefinitely. If it fails, even slightly, while you're inside the throat, the tunnel closes, and you're in it. The tidal forces, the differential gravitational pull between one end of your body and the other, would stretch you along the tunnel's length while compressing you from the sides simultaneously. Physicists call this spaghettification. It's the same thing that happens near a black hole's singularity, and the name is accurate in the most disturbing way imaginable. You don't explode, you elongate, molecule by molecule, drawn out into a thread of matter so thin it barely qualifies as matter anymore. But wait, that's not even the terrifying part. Let's get specific. Let's put you inside. You've crossed the threshold. The wormhole mouth is behind you. Ahead, the far end glows faintly. Another location in the universe, impossibly distant and impossibly close at the same time. Your eyes are receiving light from two completely different sections of the cosmos simultaneously. Your visual cortex doesn't have a protocol for this. What you'd see is a tunnel of impossible depth, both ends visible at once, neither one appearing closer as you move. Your skin registers nothing unusual, yet. Then the exotic matter fluctuates. Not catastrophic, not yet. A 0.3% variance in the negative energy field holding the throat open. Less than 1%. But here's the thing. 1% of the force required to hold back the gravitational collapse of spacetime is not a small number. Not even close. The walls of the tunnel, the curvature of spacetime itself, tighten by a fraction. Your spine registers pressure it has no category for. Not impact pressure, not fluid pressure, geometrical pressure. The pressure of space itself getting smaller around you. Your bones wouldn't break. They'd compress along 4 dimensions, not 3. And the sensation wouldn't be pain exactly, because your nervous system evolved to handle damage from external forces, from heat, from cold, from impact. It did not evolve to interpret what happens when the geometry of the space your body occupies turns hostile. Scientists didn't believe tidal forces inside a traversable wormhole would be this severe at first. Then they ran the numbers. Even a wormhole stabilized by exotic matter still creates tidal gradients near its throat. And at human scales, those gradients are lethal unless the throat radius exceeds several kilometers. Several kilometers of open, stable, exotic matter-supported wormhole. We've never produced a single atom of exotic matter at anything close to that scale. And this next part is the reason I can't sleep. Here's where the wormhole stops being a physics problem and starts being a philosophy problem. General relativity doesn't just allow wormholes to connect 2 places in space, it allows them to connect 2 places in space-time. That means not just 2 different locations, but potentially 2 different times. A wormhole whose 2 ends are moving relative to each other at high velocity or sitting at different gravitational potentials will develop a time difference between its mouths. If one end has aged 3 years less than the other, which is entirely permissible under special relativity's time dilation, then stepping through doesn't just move you across space, it moves you across time. Stephen Hawking proposed what he called the chronology protection conjecture. Not a proven theorem, a conjecture, a hope. His argument was that the universe appears to prevent closed time-like curves, time loops, because the moment a wormhole became a time machine, quantum fluctuations of radiation would amplify at the opening into a feedback loop powerful enough to destroy the wormhole entirely. The universe, Hawking suspected, enforces its own rules, but we don't know for certain, we can't test it, and here's where it gets worse. If a traversable time-connecting wormhole could exist, and the math doesn't forbid it, then the version of you that comes out the other side might arrive before the version of you that went in. You could, theoretically, shake hands with yourself. Wild, right? And every physicist who seriously modeled this agrees on one thing. That interaction is either a paradox that tears the wormhole apart, or evidence of something even stranger. A universe that branches, that spins up a separate timeline just to absorb the contradiction, rather than letting the paradox exist. The universe doesn't break, it forks. Okay, assume you survived. Assume the exotic matter held. Assume the throat was wide enough, the tidal forces manageable, the time differential small enough that you didn't arrive before you left. You exit the other mouth. And here's the single most staggering fact about wormholes. The one that gets completely lost every time people debate whether they're even possible. The 2 mouths of a wormhole can be separated by billions of light years in the space we perceive. The tunnel between them, the throat you just traveled through, might be only meters long. Billions of light years in our space. A hallway through the wormhole. Get this, you haven't just traveled across space. You've revealed something fundamental about what space is. That the distances we perceive, the vast, cold, overwhelming distances that make the universe feel lonely and unreachable, they're not fundamental. They're a feature of this surface, this 3-dimensional layer we happen to exist on. Underneath it, through it, the universe might be far smaller than it looks. Every star that feels permanently out of reach, every galaxy too far to ever visit in a human lifetime, or 1,000 human lifetimes. Every civilization that might exist on a planet orbiting a sun we could never reach across any generation of our species. A wormhole says, that's just a perspective problem. We're a species that's been staring at the stars for 100,000 years, telling ourselves the distances are the point, that the universe's scale is the whole story. But maybe the scale is the illusion. Maybe the universe is far more intimate than it appears. And honestly, that's the most hopeful and terrifying thing physics has ever suggested. That Einstein in 1915, not as a prediction, not as an experiment, just as a consequence of following the math wherever it went, was already leaving us the directions. We just weren't ready to believe it yet. Here's the hard truth. Right now in 2024, we've got no confirmed wormhole, no detected exotic matter at the required scale, no traversal, no proof these structures exist anywhere in the observable universe outside the pages of general relativity. But the equations allow it, and in physics, allowed has a way of eventually meaning found. Nothing in the universe that the math permits has stayed hidden forever. Nothing. Absolutely nothing. The universe isn't hiding wormholes from us. It's just waiting to see if we're smart enough to find them. If that left you staring at the night sky a little differently, subscribe. Because next time we're going somewhere even stranger. What happens if you fall into a wormhole isn't just a physics question. It's a question about the nature of space, time, and whether the universe is as large as it appears. In this video, we walk through the real science of Einstein-Rosen bridges, how exotic matter would need to hold them open, what tidal forces would do to your body inside the throat, and why wormholes might not just connect two places in space, but 2 points in time. We cover the chronology protection conjecture, the Casimir effect, gravitational lensing, and what general relativity actually predicts about traversable wormholes. This isn't speculation dressed as science. Every claim here comes from verified physics. And the most staggering part? The math doesn't forbid it. Subscribe for more videos that take the hardest ideas in space science and make them feel real. Wormhole. Wormhole explained, what is a wormhole? Einstein-Rosen bridge, traversable wormhole, exotic matter, space travel, general relativity, space-time, tidal forces, spaghettification, time travel physics,